So last time we ended with this talk about certificate authorities. I just want to briefly remind you what certificate authorities are so we can do this demo that I ran out of time for last time. So with HTTPS, the first thing we had to do is have this key. We have to get the server's certificate, their public key. I guess this is before we talked about certificates. But we have to get their public key somehow, and we need to get that in a secure way. There's one big danger here. If somebody's tapped into, sounds weird when I say it like that, but like tapped into the internet, or if they have like a fake router, you could have bring in your router. Don't do this, please. Bring in your router and name your Wi-Fi network UB Secure. I mean, people might connect to you. And you can start grabbing passwords and doing like man-in-the-middle attacks and some nasty stuff. Or if somebody has access to a router, you know, there are a lot of ways to pull off a man-in-the-middle attack that you should definitely not do. But to make sure that you're not subject to this attack, we have something called certificate authorities. So instead of the public server, or instead of the server just sending you their public key, which cannot be encrypted, you know, we could come up with some grand scheme or something, but this is the solution that we have in place. They can't encrypt that because how are they going to encrypt that traffic before any keys have been exchanged? They could do that by asking us for a public key, but how do we send that public key without it being encrypted? Like, those can't be encrypted because something has to be communicated before we start encrypting, and that's at least somebody's public key. Somebody's public key has to be communicated over the internet in order to encrypt anything. You can't encrypt anything before that. So what we do is, instead of communicating public keys directly, we're going to communicate certificates. Certificates contain the public key, except they're signed by a trusted source, and we have to assume that that source is trusted, and that source is going to be a certificate authority. So the certificate authority is going to be a trusted, known source of encryption, and we're going to assume that we have the correct public key for these sources. So we're going to assume that the public key we have for each, what we'll end up calling a root CA, that we have a valid public key that has been securely communicated to us. That usually happens during installation processes. They're verified, and you know, we make sure that those are secure. It happens during your operating system installation. I keep saying browser installation, but I have to back off on that one a little bit. I don't know if the browsers control these. I think it's at the operating system level where we get these certificate authority public keys, or certificate authority certificates. They contain the public keys. So we have these certificate authority public keys, and then when we get a certificate from a server, it's signed by one of these certificate authorities. So if I'm going to start a website, I build up my website, I go to deploy, add a domain name, and then I say, hey, certificate authority, I control this domain name. I have to do something to prove that. And then the certificate authority is going to issue me a certificate which contains my public key and a signature of theirs to verify that that is the public key, that I can, and then I can share that certificate with everybody and say, look, I went to a certificate authority, I proved that I'm the owner of this domain name. They signed my public key. Here's my verification from that certificate authority saying that I have, that this is the public key associated with this domain name. And when we come back from break, I'll give a demo of that. There's, Let's Encrypt is a fantastic tool. It has a script, you just run it on your server, and you get your certificate. It's super easy. It even installs it for you. The way that works is you run that script on your server. It'll communicate with Let's Encrypt's servers, and then they'll send information to your domain name that you're claiming, that you're attempting to claim. And if that script communicates with their server through that domain name, they can verify that you do control that domain name. And then if that doesn't work, it's going to give you errors and not give you cert. But if it does work, it's going to say, yeah, verified that you have this domain name. It'll actually run a mini server and generate random secrets, put them on that server, and then connect to that domain name. Make sure that domain name routes to your IP address that's running that script, and it'll verify that you control that domain name. If you don't control that domain name, I don't see how you're going to spoof that, because that domain name is going to route to something other than your router. You'd have to spoof DNS records, or, it's hard to spoof. So we're going to assume that that certificate was signed by the CA for the legitimate owner and controller of that domain name. And then that's the certificate we share to all our users. We say, here's my certificate. It's signed by the CA using their private key, so everybody can verify the signature. And a hash of the entire cert is also stored, so they can verify that the certificate has not been tampered with. So you take the cert, hash it, make sure it's minus the hash itself, make sure that matches the hash to make sure that that certificate has not been tampered with. And then you take the signature, decrypt it with the CA's public key, and make sure that signature checks out as well. If both of those things check out, you have a valid certificate, and you can use that public key in that certificate to communicate with this server. These are extremely hard to fake, unless you have the CA's private key, of course. Or somehow you get your public key stored as a legitimate root CA on everybody's devices, then things get bad too. There was at least one, I don't remember the details of the story specifically, but a CA was compromised. It's very rare, but a CA was compromised at one time, and there were a bunch of fake certs that were out there. The certificate, the root CA cert, had to be revoked, and it causes a mess. So this isn't flawless. There is that assumption that the root CA's certificates were communicated securely and that they have not been compromised. But if that assumption is true, everything else builds on top of that, and our whole chain of logic flows to having secure communication over the internet. Again, assuming that nobody broke factoring or a discrete log. Of course, those will break everything as well. So the root CAs, the ones that are pre-installed on our machines, those ones often don't actually issue certificates. The root CAs end up offering certificates to other CAs, non-root CAs, and then we can go a few layers down the chain until there's a CA that's actually issuing certificates to our domain names for us to use for our websites. So this generates what's called a certificate chain, or a key chain. So the root CA will sign the cert for a CA, which might sign the cert for another CA, and however many steps along the chain it goes. And then a CA will sign the cert for an actual domain name. And then as long as you get a cert for a domain name, which probably won't be signed by a root CA, but as long as the key chain ends at a root CA, we're going to say that certificate is valid, that it's a legit certificate. If it doesn't end at a root CA, we got some problems. If it doesn't end at a root CA, that's when your browser yells at you and says this is what's called a self-signed cert. If it's a self-signed cert, it means it can't be verified by any root CAs, and you shouldn't be trusting that cert unless it's your self-signed cert. Like I always click, yo, it's okay, I know this is a self-signed cert, usually when it's my app that I'm developing, because I signed the cert, and I didn't want to get a domain name just for local testing. That's the often reason why I'll be okay with self-signed certs. So it's not the worst thing in the world, but if you see self-signed cert and you are not the owner of that app, proceed with caution. So we can look at our certs. So I can go into my certificates. We started at the browser, but we ended up at the OS level. And I can see all of the certificates. Sorry, I can't really zoom in on this one. And I can see all of the certificates that are installed on my machine. These are all of the root certificates. A lot from Apple. Seems like it's missing a lot. So, because I'm not at root CAs. Those are local CAs. So here's all the root CAs that are installed on my machine. If you look at your root CAs, you're probably going to see almost an identical list. You should see the same root CAs that we see. And these expire in very lengthy times. We assume that these are secure. That's a strong assumption, so we don't want to go through that process like every year and reissue. Like, how do we reissue a root CA? If it's during the installation process of your OS, could we do it through updates? Yeah, but then attackers are going to start looking at those updates as an attack, a potential attack that they can launch. So these things expire in decades. So we have all these root CAs. I wonder when the next one to expire is. Belgium root CA2, global sign, a couple that are going to expire soon. December 15th. So we have all these root CAs. So every certificate that I see has to be signed by one of these root CAs. Yeah, I want the Wikipedia page on it. What the hell? Oh, I feel so old when I do things like this. Screen magnifier? Yeah, I'm going to cut my losses on that one. So then we can go to a website. I'll pick on my own website. Click this lock here, and you can actually see the certificate for any website. We're going to click on the lock. We're going to go to certificate. I have a valid cert, because I hope I have a valid cert. And actually, you know I have a valid cert because I didn't get any warnings when I went to this site. You'd see all kinds of warnings. The internet doesn't like anything that's not HTTPS anymore. And if it's not a valid cert, it's effectively not HTTPS. So I can look at all the details of this certificate. I can see the domain name for the certificate, CSE312.com. Certificates are always attached to a domain name or a subdomain name, or what's called a wildcard cert, which accepts it for every subdomain of a domain. There are different types of certs, but they're always associated with the domain name. It's issued by Let's Encrypt. It uses SHA-256 and RSA encryption. It's somewhat a coincidence. There are a few other ones out there, but the certs from Let's Encrypt happen to use the algorithms that we looked at in class. Kind of coincidence, but the algorithms I show you are actually still used. Don't let somebody tell you SHA-2 is outdated because SHA-3 exists or RSA is old. Those people are just, I don't know why they say things like that. But you can see clear as day, those algorithms are used today. When it's valid, when it's expiring, not valid after January 5th. So over winter break, I'm going to have to reissue this cert. Hopefully I have everything set up so it's going to be automatic. But sometimes things don't go the way I want. I've had certs expire and not auto-renew. But I have it set to auto-renew, so I shouldn't have to take any action there. The public key is an RSA encryption key. It's a 256-byte key, and there's my public key in the certificate. Those are the bytes of my public key. If you want to encrypt things and send to me, there's the public key that you're going to use. There's my value for N. So this is E, and this is N. N is 65K here-ish. And the key size, I always forget how this works. The public key is 256 bytes, but it's just times 8, isn't it? Yeah, that's just times 8. It's bytes versus bits. A 2K bit key size, which would be 256 bytes. I was looking at that, I had a brief pause, like, wait, bytes versus bits. The signature, to verify that this was issued by Let's Encrypt. And then a whole bunch of other information. I'll skim over the rest of it. And the fingerprints. So hashes of the cert itself. We got 2 different hashes. If somebody wants to break this one, one hash is secure enough, but spoofing 2 hashes, finding 2 hash collisions simultaneously for 2 different hash algorithms, oh boy, good luck. They ain't spoofing that. So this was issued by R3, Let's Encrypt R3. So if we go to our keychain, I can look through this all day. I'm not going to find Let's Encrypt R3. Let me check the L's. If I know my alphabet, there are no L's, right? R's, let's look for R3. There are no R's either. They're really trying to make that one hard for me. No R's either. So nothing that starts with R, nothing that starts with L. So let's encrypt R3. Not in my keychain. Oh my, that's a problem. But no, we remember that that's just not a root CA. Intermediate CA. So this is a certificate authority with its, that is signed by issuer, that's signed by ISRG root X1. It's got root right in the name. I know that's going to be a root CA. So this CA issued Let's Encrypt CA. So if we look for that one, it's going to be right up here in the keychain. This is our keychain. We can see ISRG root X1, root certificate authority that expires in 2035. We can see all the details of that. We can see their public key, which better be a huge key. 4K key. They better have huge keys because attackers have decades to try to crack that key. So they better have really huge, very large keys. If we look at the keychain, ISRG root 1 better be in there, and there it is. There's my root CA that is the source of truth for encryption on CSE312.com. So if you go to CSE312.com and you don't get any warnings, no flashing signs that say, holy shit, this site's not secure or anything, that means you have this cert, this exact cert with this exact public key installed on your machine. So this key was distributed to all of us, different OSs, different browsers. You still have this exact CA down to the absolute bit of, where are we? It's not going to show me. Down to the absolute bit of this public key. This public key, these 512 bytes of information, you have those exact bytes somewhere on your machine. If you can visit my site without getting warnings, you have that exact root CA's public key, their certificate, on your machine. You might not have this intermediate one, this R3, but it's verified by the root CA. So everything's good. We're feeling good about security there. You can do this. You can look at other sites. Like if you go to Google, they're using elliptical curves. I'll try to do this kind of quick and not spend too much time because I know it's hard to see up there. Their certificate, Google, oh, not issued by Google, GTS, unless GTS is Google. Yeah, Google Trust Services. Yeah, so Google's self-signed. They're big enough. They get away with that. SHA-256 with RSA. Okay, I was wrong. No, yeah, elliptic curve. Oh, signature algorithms. And then the public key is an elliptic curve key. Just kind of like the newer thing. It's not objectively new. It's been around for, I don't know, maybe a decade, at least 5 years since I first started hearing of them. So not necessarily new, but it's like the cooler way of doing encryption. I don't know how to say it. It's just like the newer thing. It's one that Shor's algorithm doesn't break. So as long as you have that keychain and it's valid, you have some good old HTTPS on your server. So what exactly is HTTPS? And don't worry, there are still going to be more problems with this that we have to resolve. That we haven't answered yet. So let's talk about it. HTTPS is just shorthand. It doesn't really exist. It is really a thing. It's just easier for us to say. It's really HTTP over TLS. That's what we mean when we say HTTPS. So HTTPS, secure HTTP, or HTTP secure, if you want to use the common names. HTTPS is encrypting all of our data, but without hindering HTTP. It really is just HTTP. This is why I like HTTP over TLS. It really is just HTTP. We're just communicating our requests and responses over the TLS protocol. So TLS is going to sit in between the TCP socket and our HTTP server, and it's going to encrypt all the communication. After it leaves the world of our app of HTTP that speaks HTTP, messages leave that world, go through this TLS layer, it gets encrypted, and then goes to the TCP socket. So the TCP functionality, everything TCP does, everything HTTP does on either side, work exactly the same. This code is completely encapsulated to sit in between them, and either of them work without even caring that TLS exists or is there. When information comes from the TCP socket, it goes through this TLS layer, which decrypts and then sends it to our app. So our app doesn't care, no web apps actually care that when it sends information over the socket that it's encrypted. So everything we write, we just think in terms of HTTP, we worry about the app itself. We don't have to retroactively change everything to add security to it. It just happens when we slap that TLS layer in there. TLS used to be called SSL. SSL is the older version. You hear anybody talking about SSL and TLS, and they start throwing around two new three-letter acronyms because we love these three-letter acronyms. SSL is the same thing as TLS. It's the same exact library. They just renamed it after a while. And SSL is outdated. Most sites won't support SSL just because it's too old of a version of TLS. I think even TLS 1.0, I believe, will give you warnings if that's all if you have a really out-of-date browser that doesn't support TLS 1.1. I think you get warnings at most sites. Most sites will be like, nah, this ain't cool. And at this point, Google probably does what they like to do and say you can't use it if you're using Chrome. No, that doesn't make sense because you'd have to have an out-of-date browser to be an out-of-date Chrome. SSL was renamed to TLS. So there's nothing after SSL 3.0. They renamed it TLS 1.0. So I always refer to it as TLS because that's just what it's called these days. TLS, visually, is going to sit right in between HTTP and TCP. It's a whole other layer in the protocol stack, and it's completely encapsulated. The nice thing about the network stack, the layers of network protocols, is that they all work completely independent of each other, completely encapsulated, makes it easier to think of these pieces one at a time. We spend most of this class right here. We talk about these just a little bit. We're talking about TLS a little bit here. And then you can go take modern networking concepts where you'll talk about IP and TCP without caring about HTTP or TLS. I don't think they talk about TLS in that class. So we can teach you one layer of this network stack at a time because they're nice and encapsulated, a concept that we love in programming. We love encapsulating things so we can think about one thing at a time. It's very, very beneficial. I don't want to have to think about the whole network stack every time I add a feature to my app. That just, like, if I'm adding WebSockets, I don't want to have to think about how this affects TCP. I just say, oh, it's still using the TCP connection, not touching TCP. I'm just using that with a different application. I don't have to rethink how I'm using TCP. Very nice features. When I add TLS, our WebSockets, the WS protocol becomes the WSS protocol, and I don't think about it beyond that. Just secure after that. Like I've really hammered that point home. I don't need to say that again. All right, so I promised you there'd be another problem, and there's another problem. What we want is two-way encrypted traffic. That's what we want. We want to be able to send encrypted traffic to the server. Server sends encrypted traffic to us. Cool. We get the server's certificate. We get their public key. We want to send a request to the server. We encrypt that request, send it to the server. The server decrypts, reads that message. Cool. Everything's fine. Everything's encrypted when we're sending something to the server. But how's that server going to send encrypted traffic to us? Is every single user going to go to a certificate authority and get a signed certificate to send to the server that they're connecting to? Is that how we're going to do things? I mean, we could do that. Is that how we're actually going to do this? Of course, the answer is no, the way I framed it, at least. Should make it clear that the answer is no. So what we're going to do, what TLS brings to the table, is another handshake. So we're going to have the TLS handshake, where the server and client negotiate how they're going to encrypt traffic. TLS is actually a very flexible protocol. TLS itself doesn't define much of anything. If you look through the protocol, I'll go over like at a very zoomed out level here. But if you go through the protocol doesn't specify much of anything. It just specifies the steps of this handshake, and then each step can be modified to whatever encryption algorithms are cool for that day. You know, as new algorithms come out, we don't want TLS to get outdated. So as new protocols come out, TLS is generic enough that it's just going to handle those new implementations, and they'll have to fit the TLS handshake protocol. So during this handshake, we're going to agree on a symmetric encryption key, which means that we have one key, not as opposed to a public-private key, a public key encryption system. TLS is going to negotiate a symmetric key, which is going to encrypt and decrypt. The client and server are both going to have that symmetric key, and they're both going to encrypt and decrypt with that same key. So what we need is for a client and server to agree on this symmetric encryption key, and that's what the handshake's going to do. So we have the goal of securely agreeing upon that symmetric key. So to do that, there are a lot of different algorithms. TLS is flexible enough that the next algorithm comes out and we can all start using that one. I'll go through one of them, the Diffie-Hellman Key Exchange. So Diffie-Hellman Key Exchange goes through this process, which will take a couple of slides. We're going to agree on a prime number P that generates a group G, and these are going to be public values. Everybody can see what P and G are. An attacker eavesdropping, eavesdropping on this, watching everything that's going down, they get P and G for free, public information. We're going to agree on P and G, which can all happen publicly. They're public, so we don't have to really worry about anything for those. And they're going to be generated such that P generates the group G. What that means is for every value 1 to P minus 1, we're going to get G to the I mod P is a unique value. So if we take G and keep continuously multiply it by itself, first we're going to start with G. I should include, one of those should be a less than or equal to. We raise G to the power of 0, we're going to get 1, it's a unique value. We multiply that by G, we're going to get G. We're going to multiply that by G again, get G squared mod P. At some point, we're going to be larger than P, probably after the first step. So we're going to mod that and get some value between 0 and P minus 1. What a generator means is that we're going to get to every value. We do this, multiply G by itself, P times, or P minus 1 times. We're going to get every single value from 1 to P minus 1. So we say that P generates the group G because it kept giving us unique values. It didn't get cut in a cycle. If it ever gets caught in a cycle, then P raised to some power is going to give us any number of powers, isn't going to give us the full range that's possible. If it's a generator, it gives us this full range, 1 to P minus 1. So it gives us a lot of unique values. It fills up that whole group of P. I feel like I said one of those backwards a little bit. G generates P. And then, so if we multiply G by itself, P minus 1 times, we'll have that last unique value. We multiply G again, we'll get back to G itself. It'll wrap around on itself and then continue the process again. So those are nice properties. If you study abstract algebra, that's a really nice property that we want for values very often. We want these generators. It's a really powerful mathematical concept. After that, once we agree on P and G, the client and server are both going to generate just random numbers. We'll call the client's number A, the server's number B, and these are both private. I'll call them super private even. These values cannot be communicated to each other. The server will never know A, the client will never know B at any point during the key exchange. This is important for one reason, well, I shouldn't say that one, but I'll just say one reason. I was going to give two, but I don't really like the other one. It's important for one reason, is that they never have to be communicated. A and B are never sent over the network. So these, A and B, an attacker can't see these. They can't know these because they would have to hack into your hardware itself. don't get communicated over the network. So the client is going to compute G to the A mod P, send this to the server. The server is going to compute G to the B mod P and send that to the client. And then when each server and client receive that value from the other, they're going to raise it to the power of their secret value. So now client and server both have this value G to the AB mod P. They both have the same value, and we've securely agreed upon a secret value. So we both have G to the AB mod P. The only things that were communicated over the network were G to the A mod P and G to the B mod P. But as we know from last lecture, solving this, the attacker has G and P. They want to attack A and B. As we know from last lecture, doing that would involve computing the discrete log efficiently, which is a cryptographic primitive. So breaking those and getting A and B, not going to be easy for an attacker. It's going to take a prohibitively long amount of time to solve. So once we have this agreed upon value, we're going to either use that as a seed in some RNG to generate our keys, or just use that as a key directly, whatever the agreed upon algorithms say to do with that shared value. They're going to both use that shared value, generate the same symmetric key, or just use it as their symmetric key. And now they can start communicating, client and server start communicating using this symmetric key. A typical choice for this is the AES algorithm. AES works kind of like SHA-256, our hashing algorithms, and that just repeatedly scrambles things, but in a way that you can reverse it if you have that encryption key. The key tells you, has basically instructions on how to shuffle things around. If you throw the key at it again and decrypt it, you're going to get back to the original value. But it's similar to SHA-256 in that it does not reduce to a cryptographic primitive. There's no foundation for that security, I guess I could say. And there are some theoretical attacks for this. You'll hear people say AES is broken, never use it, because some group of researchers had one token example where they generated hash, what was it? I think that was SHA-256 actually, where they generated the two different documents that had a hash collision or something. But no practical attacks exist, at least yet. When practical attacks start being more of a threat, we'll just generate the next symmetric key algorithm. There used to be DES, that one is insecure. AES came, DES started deteriorating, people were attacking it, so AES came along to save the day, and now that's the one we use. Let's use the next one. We'll use the next one if this one starts getting practically attacked. But AES is going to be our symmetric key, is one of these symmetric key algorithms that we can use. So the TLS Handshake, at least for version 1.2, is going to follow these steps. Client hello, where the client is going to send to the server, here are all the algorithms that I know. These are coded into the browser. The browser is going to say, I know these algorithms. I know AES, I know SHA-256, but I don't know SHA-3 or whatever. Just going to say, here are all the algorithms I know. The server is going to do one of two things. It's either going to say, here are the algorithms that we're going to use for this connection. I looked through all the ones you support, and I picked my favorite ones. Here are the ones we're going to use. Or it's going to say, all your algorithms are out of date. We can't communicate because all of those algorithms you told me have known attacks. We ain't even talking. We ain't doing this. So the server can shut things down right here. If you only support out-of-date versions of algorithms, out-of-date versions, server just says no. If we're proceeding, server's going to send its certificate. It's going to say, here's my certificate. It's signed by these root CAs, these CAs that are signed by those CAs, that whole thing. Well, that's a little bit of it, just the certificate. And then the browser is going to see who signed it and then talk to that server, get their, it's going to be multiple servers involved there. But send the certificate. The whole Diffie-Hellman thing happens that we just talked about. if Diffie-Hellman is the key exchange that's being used that was agreed upon. And when the server sends its portion of the secret, which for Diffie-Hellman was G to the A mod P, or was it B? I forget which A or B I assigned to the server. But when the server sends theirs, server's B. So when the server sends G to the B mod P, it's encrypted with the private key associated with their certificate. So that's encrypted. Or not encrypted, that's signed. So we know when we get that portion of the secret from the server, we know that that came from the server. So it's signed with their private key. We verify the signature with their public key. Their public key was verified by a CA, which was verified by a root CA, which was installed with our operating system. We follow that whole chain to say this right here, that the server's portion of this key exchange, the portion of the secret that they sent us, is actually from that server. We combine our partial keys together to get the symmetric key, and then we have the symmetric key, which we encrypt back and forth. We use that to encrypt all the traffic that we send. The symmetric key is used when we're actually communicating securely, when we're encrypting over the internet. It's these symmetric keys that are used. So throughout that whole thing, I was hoping that slide wasn't the next one, but I kind of touched on this earlier, but TLS, very flexible. We have all kinds of different algorithms that can be swapped out at any point. We can use a different encryption algorithm, a different key exchange algorithm, different, we can use elliptic curves instead of RSA, things like that. TLS is very flexible in that case. But that certificate, that whole thing that we go through with root CAs and CAs and certificates, all of that was only used once during the key exchange, and it wasn't even used for encryption. We don't actually use those certificates, those public keys. We don't actually encrypt with those at all, at least if these algorithms are the ones being used. We used it for one signature. The server signed one thing, and that's it. That's all that public key is used for, is to verify that one signature during this key exchange. So we don't actually use those, the RSA, the public keys, those certificates, those things. We don't actually use those for encryption at all, as it turns out. But they are extremely important in the process of this key exchange to generate the key that we're going to use for encryption, because we verify that the server side did actually come from that server. Now, the server can't verify that our side came from us, but if there's a man-in-the-middle attack and they're replacing our secret with their own and sending that to the server, what I have that I'm going to encrypt with doesn't match that attacker's key. Whatever the attacker negotiated, those keys are not going to match. They're not going to be symmetric. What I encrypt is using a different key than what the server is going to encrypt, because the server's using the attacker's part of the secret to generate the rest of their secret. And I know that I have the server's actual legitimate secret, so the man-in-the-middle attack can't replace both sides with their stuff, because what I got from the server is verified by their signature using their cert. So the man-in-the-middle, they can replace my secret with their own, but it doesn't get them anywhere because we're agreeing on a symmetric key. The server's not going to be able to decrypt my traffic. The attacker is not going to be able to decrypt my traffic because they don't know my secret. There's no way for a man-in-the-middle attack to get anything, and we finally have some nice properties here. We can communicate effectively over the internet. There are a few other advantages to the symmetric key. One, it's a lot faster. Public key encryption is pretty slow to compute. It's not like crazy slow, but when you're encrypting the internet, like everything, there's a lot of volume there. We want things to be nice and fast. AES is nice and fast, very quick to encrypt. We don't want any delays any more delays in our messages, our requests and responses. Another nice thing we get is that these encryption keys are generated for every connection. You don't connect to a server and the server goes, we've talked before. Let's just use that old symmetric key. Now we're generating new keys constantly. We're constantly going through this handshake. So actually, if you look at how all of this fits together, when you first connect to a server, there are multiple round trips to the server and back before you can start communicating any HTTP information. You have the three-way TCP handshake. That's a there, back, and there. And then the back would be the first step of the key exchange, which is going to be on the third step of the TCP connection, the handshake. We can say, these are the algorithms I support and start that handshake. These are the algorithms we're using. That's 2 round trips. Here's my secret. Here's my secret. Server sends its secret, which can happen simultaneously, which I guess is half a round trip. And then finally, our first encrypted request, which would be the end of the third round trip. So we got 3 round trips before we even started talking to the server. So if your network delay is like 100 milliseconds, well, that's 300 milliseconds now for the first connection. Then once you exchange keys and everything, then things go a lot quicker there. You can reuse the TCP connections. You can use that keep alive header and just send request response after that. And even if you're going through the TCP handshake, you probably generate new keys. I'd have to look that one up. If you generate new keys for every TCP connection, probably do. All right, and one more nice feature we get called forward secrecy. So one attack that an attacker could do is say, I'm going to look at all this traffic that's going around. I know it's encrypted. I can't break this yet. I don't know. I just don't know what this stuff is. But what they can do is just store it in a database. They can store all this traffic. And then maybe at some later point in time, they're able to hack into a server and steal that private key. They finally gain access. They have some like SQL injection attack that gives them root access on the, they launch a flurry of attacks, finally steal that private key associated with the server certificate. They're celebrating. They're like, all right, we're going to decrypt all this stuff now. Well, no, they can't, because all that stuff was encrypted using the symmetric key, which was different for every connection. And even having that private key, like, how is that going to help you? The only way that private key was used was to sign something. You're not decrypting anything with it. Nothing was encrypted with that. Nothing was encrypted with the public key associated with that private key. So what are they going to get? Nothing. That's what. The only thing they can get after stealing the private key is attacking new connections. They can't go back and attack anything back there. So we have this forward secrecy. We're saying, if you attack me today and steal something later, that's not going to help you. It's not going to help you here because we use the symmetric key. You can't know A and B based on that. You can only verify that the server did actually send that, which they should know that already. This is a very nice property. So even if somebody steals a private key, even if somebody steals a root CA private key, they can't do too much damage. They can only do damage until we detect that they've stolen it, and then we can invalidate that cert and stop using that cert. They can't do a whole lot of damage. They can't just go retroactively destroying everything. Very nice property. We really like this property. So a lot of really nice properties we get from just the way we do things, the way things are set up. One word of caution. So all of this is the last stuff I want to talk about, encryption. So after all of this, we have encryption over the internet. We have these key exchanges and certs and symmetric keys and encryption using the symmetric key, all this good stuff. But remember, the eavesdropper can still see your TCP and IP headers. TLS sat in between TCP and HTTP, so all of our HTTP requests, responses, the headers, the request line, the bodies, the multi-part form, all that stuff is encrypted. The attackers can't read any of our HTTP stuff. But since that layer, since the TCP layer is in between HTTP and TCP, the TCP and the IP, the stuff that's either before or after, depending on which way you're looking at the network stack, is not encrypted. In fact, it can't be. I mean, TCP, we could argue that that could be encrypted, but the IP can't be encrypted. If IP is encrypted, how are the routers of the internet going to know where to send this stuff? How are they going to know where to send something if you encrypt the destination IP address? That doesn't make sense. TCP and IP are in the open. Port numbers, IP addresses, sequence numbers, these things are all publicly known. You sniff packets out of the air, you won't be able to read the contents if it's encrypted, but the headers, you're going to know who's talking, who they're talking to, are the two most important pieces of information, and a little bit more information from these headers. This is why, even with all this encryption stuff that we're doing, this is why you still see VPNs advertising all the time. Not sponsored here today, but this is why you see VPNs all the time. This is why they're still popular, because everybody can still see who you're talking to. I could fire up Wireshark right now and see what you're doing on your laptops. If I ever become a really old cranky professor, I could run Wireshark during a lecture and see, oh, somebody's on YouTube, and then start yelling at you, who's on YouTube? I can detect that stuff. That's all in the air. It's all public information. So if you use a VPN, you can mitigate the risk there. I won't go too deep into VPNs in this lecture. Maybe we will in the last 2 weeks, the week after break if somebody's interested. But VPNs are effectively going to bounce your communication off another server. So even if you're using a VPN, I can still get quite a bit of information from you. One, I can see that you're using a VPN. Anyone within your Wi-Fi range can see that you're using a VPN. Or if they're on the other side, the server you're connecting to knows you're using a VPN. Assuming that, depending on how the VPN's set up and everything. But usually they know you're using a VPN. Most sites don't really care that much, but they are aware that their traffic's coming from a VPN, most likely. If they care enough to investigate and look into it, they'll know that. And your ISP knows you're connecting to a VPN. They're going to see all of your traffic is going to this one set of IP addresses. They know what's up. But they can't see what you're doing. They can't see what's on the other side of that VPN. So that's where you're getting some privacy. But they do know you're hiding something. So for what it's worth, just things to keep in mind. But that's all a VPN does, is bounce your traffic off another server. So just keep that in mind when you're ever wondering, is my VPN keeping me sufficiently private in this specific situation? Just think about how the traffic's going. And if you use a VPN and log into a service, you have no privacy. So if you use a VPN logging into Google, you just told them who you are. There's nothing there except for eavesdroppers. The server you're connecting to still knows. You use a VPN and log into Netflix. You just told them who you are, and they just saw that you connected from the United States, an hour ago, and then Europe in an hour. They know what's up. They can figure that out. I don't think they care so much. As long as they cover their ass enough to not be legally liable, is my opinion. As long as they're doing that much, nobody's going to come after you. But that's my thoughts on that. Let's call this one, and I'll see you Friday.